Welcome to an example in which we're going to use linear approximation or differentials to estimate the amount of paint in cubic centimeters needed to apply a coat of paint 0.04 centimeters thick to a hemispherical dome. That is so this is the volume of half a sphere, as you see down here, half a sphere, not a whole sphere, with a diameter of 8,000 centimeters. Okay, so there's a lot going on here. So basically, here's the idea. We're gonna put paint 0.04 centimeters thick around this dome. So if you can picture, I don't know how this drawing is gonna go, but just a little layer. That did not work so well. All right, well, I'll just, oh, let me back that up. It's gonna freehand it. So basically, a little layer of paint is gonna go all around this um, over the dome, right? To a hemispherical dome. So just to the top, not to the yeah, just to the top, all the way around. It's a half a sphere, right? And we're doing a coat of paint, and the thickness is 0.04 centimeters. So that's a volume of paint, isn't it? It's volume. It's three-dimensional. So we got to use the volume formula for the volume of half a sphere. It's going to be half of a sphere. So the volume formula is half times, what's the volume of a sphere formula? 4/3 pi r cubed. It's r to the third power because it's, three-dimensional. So there's the formula for a whole sphere. So we put the half in the front. We have half a sphere. Half a sphere, a hemisphere. Hema means half, right? Hemisphere, half a sphere. So, okay, so there's the volume formula. And so we want to know how the volume changes, volume of paint, as you put a layer of paint all the way around it, it's going to grow, the volume's going to grow. So really we want the derivative, don't we? We want dV dr because, and we know it says differential, so that's obviously the big clue. Want to know, how does the volume change as the radius changes? We'll get to other things in a minute, right? Because what's going to happen? Here's the radius on the diagram. The radius is going to get thicker. When you put that paint, that 0.04 centimeters of paint, all the way around the dome, the radius is going to grow a little bit. There's going to be a change in radius. It's going to get thicker. All right, so here we go. It's going to be, I'm going to make this 4, 6. I'm just going to multiply 1 times 4, 2 times 3, pi. And now this 3 is going to come down. 3 r squared, subtract 1 from the power. Good. And then I'm going to multiply both sides by dr. dr cancels out. So dv is, and then this 3 is 3 over 1, so it's going to go to the top. So it's 12 over 6 pi r squared dr. So let's be clear what this is. What is dv? The difference in volume, and dr is the difference in radius. Okay. So we want to know the difference in volume, like how much volume of paint, right? The amount of paint, the volume of paint in cubic centimeters. That's what we want to know. What is the difference in volume? When we added this layer of paint, it changed the overall volume, and that change, that added volume is all paint. So that'll tell us how much paint. The change in volume is how much paint. So, okay, so we've got to plug in. This is just a 2 pi. Now right here, r squared. What is r? What's the radius? Well, now we're going to get down to business a little bit. It tells us all the way across this thing, all the way across. Well, here, you just can't see that color very well, huh? All right, let me change it. So all the way across is the diameter Diameter means all the way across, and that is, they told us 8,000. So 8,000 is all the way across. So the radius, therefore, must be 4,000. It's half. So right here, that's going to be 4,000. Okay, so the dV, difference in volume, is 12 over 6, which is 2 pi, and this will be 4,000 square here. Let me get more room there. Yeah, not doing it so well. 4,000 squared, and then the trickiest part. What about dr? What's dr? Well, that stands for difference in radius. How's the radius going to change when we add that layer of paint? Now you might say, well, it's 0.04. Well, no, actually, it's the um the 0.04. We're going to apply a coat of paint 0.04 centimeters thick. Oh yeah, so I think it is 0.04, isn't it? Yeah, because this will go out, the radius will go out 0.04. Yeah. So the change in radius, excuse me, it's just that 0.04 because it gets thicker, right? The dr, change in radius, must be 0.04. They might think, yeah, well, they're adding 0.04 to this side and then all the way around, so it's going to be 0.04 on the other side, right? So yeah, well, but still, the radius from the middle to the edge, that's what radius is, middle to the edge, will get larger by 0.04 for that layer of paint. All right, so there it is. Let's hit the buttons on our calculator. We'll get our hands on dV, the change in volume, and the change in volume is because of the paint added, and so that tells us how much paint. So 2 pi, 4,000 squared, 0.04. 2 pi, 2 pi times 4,000 squared. Did I do that right? 2 pi, 4,000 squared, 0.04, right? Equals. There's a number, what is that? 4,021,238. 4 million, yeah, there it is. 21,238.60. Is that like exactly right? 0.597. So yeah, rounds to 0.60. Good enough. That's how many. Oh, and that's cubic centimeters because, and it even said it right here, because that's volume, cubic units. There's always volume. Like cubes are three-dimensional, they have volume. Cubic centimeters of paint. That's an estimate. Again, it's an approximation. Why? Well, because when you do DVDR, you're doing derivatives, which you're really doing tangent line. We saw in this whole chapter, in this whole section, I mean, how tangent lines are approximately the same as the original function when you're close to it. Are we close to it? Yeah. The radius is what, 4,000. Diameter was 8,000. Radius was only 4,000. We're only off of that by 0.04. Change in radius is very small. So we're right around it whenever you're really close to the original R value or whatever your letter is. The derivative, the tangent line, is a very close approximation to the change in the actual function. So it's not exact, but it's a very close approximation. And so there we go.